Hi everyone, thanks for joining me for this video today. I'm recording this live at the school, so one, I might make some mistakes, but also you might hear some background noise going on, but I'll do my best. So the purpose of this video is to give new parents an understanding of how we do math at Pear Tree, and bear in mind this is just one example I'm giving you. Different classes of different age groups and different themes will have so many different methods of teaching in terms of like the variety of how we go about doing things, but this will give you a snapshot. And another reason for this is to give you an idea of how high level the math is here, but done so in an age appropriate way. Traditionally, parents will feel like unless you're doing multiple grades higher level math, you can't possibly challenge kids, and that's simply not the case. Whenever you put math in application and you're actually using it, it immediately becomes far more challenging, and this will illustrate that perfectly. And I think you'll see that even if your kid can do multiplication, they will not be able to do what I'm about to show you. So let's get started. So this is going to be an example from our urban farming theme, which we're teaching at the very moment I'm recording this video for a grade 4-5 class. They've been learning about different types of farming, whether it's agricultural farming, livestock farming, and basically different types of farming. And in this case, this was something they were challenged to work on in terms of raspberry farms, which is something that actually takes place here in BC. Therefore, it's very locally relevant. And the facts that you see below that I just highlighted are actually real facts. These are numbers that have been taken off the internet related to raspberry farming here. There are some mistakes with this worksheet with the strawberry and strawberry bushes on the bottom left, but everything's meant to say raspberry bushes, which is the most important thing anyway. So this is the information the students were given. They were told they have a raspberry farm with 10 acres in size. Each acre holds 2,200 raspberry plants, and each bush costs that much. And after 1 year, you get that much of a yield, and you can sell them for that much money. So we're not going to do all these questions. I'm just going to choose a couple of examples here, and you'll see immediately how much more challenging this is than traditional learning. So the first question the students have, the top left, is how many raspberry bushes do you have in total? So when they get this question, they have to be able to pull the facts out of the information below. They have to know what they're looking for, and therefore what formula there is they're trying to solve. So there is no cookie cutter formula here that they're given. They have to decide what the formula is and then still solve that formula afterwards. So the students are going to be thinking to themselves, or should be thinking, well, I know that there are 10 acres and each acre holds 2,200 plants. So that must be 10 times that amount. So they would write 10 times 2,200, which is 22,000. And ideally, they would label these numbers to say what these numbers are referring to so they don't get confused. And also, if they're asked, well, 2,200 what? They can actually say that's the number of plants, raspberry plants, just like with 22,000. The next question, how much would each acre cost to plant raspberry bushes on? So now this gets far more challenging, because now you're thinking in terms of cost, but the cost is in cents. So you've got 67 cents. So now we're working with decimals. So they know that 1 acre has 2,200 plants, and also learning things like that. Has means equals, and costs means equals. This English language translates in mathematics as like plus and minus and equals, etc. And so each plant costs 67 cents. So that if they're working with cents, they're now working with decimals. So they end up with this horrible formula. And there are many ways to solve this. Traditionally, you would have to just solve this as you see it right now. But we teach in our school for students to be flexible math thinkers, and also to be very numerically literate. In other words, to know what they're looking for, but also to know when something goes wrong as well, so they can spot their own mistakes. So when I look at this, and this is one method I would teach if I were teaching the class, is I would say to myself, when I see 0.67 multiplied by something, I'm telling myself that I'm calculating 67% of that number. So if you were just to do this on paper rather than with a calculator, then one way to solve this would be to break the number 67% into its components, which would be like 60 and 7. But then to get to 60, to work out what 60% of a number is, you could start with something simple like 10%. 10% of any number is the same number with a zero removed. So 10% of 2200 is 220. Then you can work out 20% is, because that's double that number. 30% would be the 10% plus the 20%. So you've got 660. 60% is double that. So now you've got 1320. So that gives us 60%. And now we do the same thing working out with 1%. 1% is the whole number with 2 zeros removed. So now we're down to 22. 6% is 6 times that. Which you could do the way I just showed you before, where you're doubling the number and doubling it and then adding the numbers together, or you can just literally do 6 times that and come up with the answer 132, and then add those two numbers together to 154. So in total, the 67% is 1320 plus 154, which is 1474. So we've got our answer, but there's another way they could have calculated, still not requiring decimals, and that's to think in terms of a whole number approach. So in other words, instead of thinking about 6.67, they think about 67, and that the answer would be whatever 2200 is multiplied by 67, it's 100 times less than that. It's 2 place values less than that. So now it's much easier because now they're working with these whole numbers instead of decimals. They're much less likely to make mistakes with their place value than if they're working with decimals. So now they're working with this number, and they could just calculate it the traditional way, where they just leave everything where it is and then just figure everything out on the spot. But they're still likely to make some mistakes here, because when you start working with 60 times a number, you can still put numbers in the wrong columns, because you start thinking in terms of, a lot of kids, especially in traditional schools, will not say that's 60, they'll say that's a 6. And so as soon as you start consciously thinking of a number as a 6 rather than its true place value, you will start saying 6 times 2 is 12, and then where do you put the 12? Because you're not thinking in terms of its actual value in terms of those numbers. So we teach through a place value approach of a whole number of, and also thinking what these numbers are. So you can break these numbers apart. You can say you're working out 60 times that number and 7 times that number. You could even go one step further and say it's 6 times that number and then multiply it by 10. There's so many ways to simplify these numbers for different levels of students. But obviously 7 times a number is a far easier thing to calculate than 60. So you start with that. And then 60 times a number, as I said, you could do 6 times a number or 60, and then you get the following number, and then you can add those two numbers together, which gives you the same equivalent to what 67 times that number is, which is, and then divide it by 100. In other words, reduce it by 2 place values, and then you would end up with the same number of 1474. So that's just 2 questions there, and I think that gives you a good idea of, just for those 2 questions, how complex the math is. And we've still got 4 more questions to do, and you can probably imagine that it's in some cases it gets a little bit more challenging for certain questions. There'll be some questions here that some kids can do, some questions that kids find easier or may use different approaches. But what we're really looking for is for kids to have a great number sense here, and to be able to show things in different ways, and to really problem solve and spot their own mistakes. And if you have the level of kind of, number sense that I'm exhibiting here, you're more likely to spot your errors than if you just go through the traditional formula approach of the one on the left and solve it, and you may get it wrong and have no idea that it's wrong because you have no place value. And even just knowing that it's 67% of 2,200, you know the number has to be less than 2,200. It's around about, half or 3/4 of that number. So you're already gauging it's going to be somewhere between 1,100 and maybe 1,800 or something like that. And so if you get an answer and it's in that ballpark, at least you know you're in the right kind of ballpark then. This next one here was related to a different activity, still connected to urban farming, but it's related to livestock. So here it's about the meat industry, and they're having to interpret data that's provided to them. So the first question asks, what is the total number of farms raising livestock in BC? So now they're not thinking in terms of percentages, they're thinking in terms of numbers. If they were only given the total and percentages, we'd have to calculate what each quantity is, but here they're given the quantities. So traditional approach is adding together a string of numbers, which is a recipe for disaster, because when you're adding together strings of numbers, you're very likely to make mistakes, because at some point you add the wrong numbers. And so we would either ask students to calculate things in a strategic way, where you add in a 6 and a 4 to make 10, and add in a 3 and a 4 to the 10 to make 17. But if you just go top to bottom and add 6 plus 3, which is 9, you're now counting past 10 from 9, and you're going to make mistakes. You're going to say, oh, that's 12 or that's 14 instead of 13, because you just made a mistake. So even just doing that is something more strategic than just adding a string of numbers together. But really, at the end of the day, we'd probably encourage students to break these numbers apart and add 2 numbers at any one time. So in this case, you've got 2 top numbers, 2 middle numbers, and then the 904 you'll add to whatever those numbers add up to. So you've got those 2 left numbers, 2 right numbers, add those together, which we did below, and then you would then add on the 904 and get the 20,037. And as I say, you could easily make mistakes if you're just adding together a string of numbers. So this is much more systematic. Okay, next one is writing percentages as decimals. Very much reminds me of what we did previous in the previous page, where I said to you that when I see 0.67, I'm thinking to myself, that's 67% of a number. And the same thing's true here, but now this one is actually making you think that way. So you've got 34% for poultry, that's equivalent to 0.34. So they should know that. This is super, super easy, but you have to get used to thinking in the sense of being able to think that things are equivalent to each other. We're not going to do that bottom question there, because that's more to do with a kind of critical thinking question. But the next question is writing each percentage as a fraction. So now we've gone from percentages to decimals, and also now decimals or percentages to fractions. Either way, it's the same thing. So you would know that as a percentage, 34% is 34 per 100, or out of 100, so that's over 100, which you can write either on top of each other or with a slash like this. It's the same thing. It's also division, so you could write 34 divided by 100. But then you have to simplify it, and you know that you can divide 34 by 2 and 100 by 2, so that's 17 out of 50. And if you know your prime numbers, 17 is a prime number, which I never remember these things, but there we are. But 17 is prime numbers. You can't simplify that any more than that. So that is the lowest possible fraction here. And that's just another example of just like interpreting data in terms of the math. But you would also start thinking in terms of, what does this information tell me? And therefore start thinking about things to do with, like, I noticed that beef is the highest selling, highest produced meat in BC. Why is that? Why is poultry second to that? So they might start thinking about facts they know about the industry in terms of, profitability, or to do with, the cost of raising them, and maybe more or less, or may require more or less space, or may have more or less regulations depending on what the animal is, etc. And they may think more in terms of ethics as well, which I doubt very much the meat industry is that concerned with ethics. But there we are. That's my impression on the meat industry. But yeah. Here's another one, and I'm not going to do these examples because there's far too many. But here's an illustration of where students could be presented with a long list of facts, which are, again, these are all real numbers connected to the pig industry, and like there's a lot of different information there about like the cost of buying piglets, which vary depending on how many you're buying. So there's obviously like bulk purchases, their weight, how long they live for, how much you need to feed them, how much they eat as they get, perhaps when they get older, how much it costs to process them, which is a polite way of saying kill them and prepare them, and also how much meat you can actually get from that specific animal. And there's just like so many different facts and numbers connected to the pig industry. So one of the questions we have here in the middle is, how much would it cost to buy 10 piglets or 10 pigs? So I've highlighted the information they should be looking for here. But even looking at this, as a teacher, I can already preempt what a lot of students will make mistakes with, because they'll see that, but there isn't a formula. So there's already a risk of them making mistakes. It says that it costs $55 per piglet if you buy 10. Now, I can probably count, I can already imagine like a certain student or a certain, the fact that not everybody in a class is going to get this answer right, even though it seems so obvious. But you can preempt that certain kids are going to look at that and just not really look carefully enough, and will go, okay, it costs $55 to buy 10 piglets. And even though it doesn't say that, they'll just come to that conclusion because they're not thinking, they're not really looking carefully at what they're reading, which is a typical problem that people have in their day-to-day lives. They don't look at information properly and they make assumptions, which are false assumptions. So here, is it 55 for 10 or is it 55 each? And obviously it's each. So what they're actually calculating is 55 times 10, which is an easy number. But if you don't read the information properly, not just the question, but the information you're provided, then you're going to get this wrong. The next question, and again, here's a potential problem. The next question says, how much would it cost to buy 30 pigs? Now, as you can see here, there isn't a number 30. So how many kids are going to be thinking to themselves, well, I know that 10 plus 20 is 30. So to work out the cost for 30, do I need to add together the cost of buying at the 10 rate and then add the 20 rate after that? Or what? And of course, anyone that knows about like bulk buying, you know that these are thresholds, that there's a 10 off price and there's a 20 off price and there's a 50 off price here. So anywhere between 10 and 20, you pay the 10 off price. Anywhere above 20 to 50, you pay that 20 off price. So if you're buying 30, you're buying 30 at that rate of the 20 off price. So you would be paying 30 times 51.50, not 10 times 55 plus that. So again, there's so much room here for students to make mistakes if they're thinking they have to add together these different amounts because they see the 10 and the 20 makes 30. And so then that's the actual question they should be solving here. And again, there's still room for mistakes, and I've already given you an illustration of how we solve these kind of questions with decimals. You could be doing 50 times 30, which you could do 5 times 30, which is 150, and then 10 times that, which is 1500. And then $1 times 30 is 30, so you add 30 to that. And 50 cents times 30 is half of 30, which is 15. So you've got 30 plus 15, which would be 45. And so there's many ways of calculating this using math strategies. You don't have to do this through traditional math approaches. And you do the same thing for the 50. I'm going to stop there though. So I think from this, you get a good idea about that. But then we go to the next stage. If you think that's complicated, try the next part. So, and I'd encourage you to actually stop the video at any point and actually try some of these activities to see how well you do in this, because it's not easy. This may say grade 4 or 5, but I guarantee you that anyone that's been through a very traditional rote approach to learning, that confronted with applied math, or suddenly like not having formulas presented to you, will be like, what am I supposed to do here? And even if you have the formula, you probably won't know how to solve it because you haven't used that math in a very long time. So put yourself in the student's shoes by trying some of these skills. But anyway, the next part here is to design a project. And you'll know that we do project-based learning through the school, but it's done as an extension of a theme. These students will have done about urban farming for an entire term, and now we'll be doing a final project connected to this. And the final project's going to apply what they've already been learning, but also extend upon this as well with more challenging skills. So here, they're trying to design a model to scale of a farm based on a form of farming that they feel that they're interested in, but also they feel like is profitable. And so they have a choice. They have a choice of different types of farming. And so for those students, and these are some examples for them of the kind of models they could build, but we would hope that they could build something better than these, even though these are actually quite good, especially the one on the right and the one on the bottom. The one on the top left is very primitive in comparison. So this is part of the work. I'm not going to show you all the work they have, but part of the work they have is to start figuring out from a board that they're given how to design the board to be to scale of an actual farm. So they would have already researched the requirements, the costs, the profitability, the space requirements for a specific type of farming. For example, Like, they might do a dairy farm or a raspberry farm or blueberry farm or something like that. And they make a commitment to doing that kind of farm. And so as a result of that, they'll then have these questions. They'll say, the first question is, how many acres will your farm be? Okay, so they may decide that their farm is going to be 20 acres based on the information they've researched. And we're just going to put that, and you don't need to know why. We're not going to answer the question why in the next second question. The third question is, what could the dimensions of the land be? So knowing your multiplication, you're thinking, well, how many ways can I make 20 using two numbers? Because 20 is actually the acreage in terms of footage or square footage. So how can I make land that has 20 acres squared? And so they'll be thinking in terms of their multiplication that you can do 5 times 4 or 10 times 2, or an extreme would be 1 times 20. And they can obviously do somewhere in between that if they feel comfortable and can make something more in proportion to the board size. But I think these two numbers here are the most logical numbers that they would come up with, and they would probably choose something like 5 by 4, which we're going to go with for the purposes of this exercise. Now they're given a board for this dimensions. They're given a board that is 60 centimeters by 120 centimeters. Now thinking about in terms of ratio, 120 to 60 is a 2-to-1 ratio, which already at this point, in terms of the next question about scale, this is a very tough question. This is technically a grade 7 question here in BC, but really at the end of the day, ratio is the same as fractions. It's the same as percentages. A 2-to-1 ratio is, one thing is 200% of the other one, or 2 times more. So it's not really any different. It's like, it's the same thing, just written in a different format, 2/1, in other words. So it's, for us, we don't think it's that much more of a challenge. It is more of a challenge in some respects, but if you've never done this before. But if you have done it before and you see that these things are all the same, it shouldn't be any more difficult for you. So 120 to 60 is a 2-to-1 ratio. Now, if you were to go for an acreage of 5 by 4 acres to make your 20 acres, that is not a 2-to-1 ratio. A 2-to-1 ratio would be like 5 to 2.5 or 8 to 4. But this is 5 to 4. And that is equivalent to 1 1/4, 1.25 to 1 ratio. So, or if you went for the 10 to 2, it would be a 5 to 1 ratio. So if you have a board that's 60 by 120, you can't say that if the bottom part is equivalent to the 4 acres, you can't say 120 centimeters is the 4 acres, because you are not working with the same proportions. You're just arbitrarily telling yourself that length is 5 acres, and you end up with a disproportionate scale or disproportionate board. You have to then, if you commit to 60 centimeters being equivalent to 4 acres, you have to calculate how much of that 120 centimeters is equivalent to 5 acres, which is where the scale comes into this. So if 60 centimeters is equivalent to 4 acres, then half of that is equivalent to 2 acres. And half of that is equivalent to 1 acre. So in other words, 1 acre is 15 centimeters, which is a 15-to-1 ratio. So if you know this, if you know that 1 acre is equivalent to 15 centimeters, then 5 times 15 centimeters is equivalent to 5 acres. So I've written on question 4 there, I've written that 15-to-1 ratio, which is what we're working with here for this board, and 15 centimeters is equivalent to 5 acres. So with our calculations here, we can go back up and we can say that if 60 centimeters is equivalent to 4 and 15 centimeters is equivalent to 1, then 5 is equivalent to those two numbers added together, which is 75 centimeters. And you can see from my diagram that I've put on the top there, it's considerably less than the full length of the board. And so therefore now we're working in terms of proportion, but also working in terms of scale. We're working in terms of both. And that is very, very, very difficult for a grade 4 or 5 student. And yet we're still working with essentially grade 4 5 math, and yes, you could argue that ratio is grade 7, but there is no difference between percentages, decimals, fractions, and ratio. They're all one and the same thing. So it is really, at the end of the day, grade 4 5 math. And I wonder how many of you, like watching this as parents, could have solved this and could solve the rest of this paper and could actually come up with this board and all these facts. And this is just the first stage of this. The next stage is then to start thinking about like the costs, some of the requirements you need for the land in terms of like storage space, in terms of like how much money you're going to make. So there's so much involved in this project beyond just designing the board layout. And so you can imagine how challenging this is for them, not only to design, but then to actually explain to their parents after in a way that they can actually demonstrate their understanding of this. It's very difficult, and I hope from this video you get a much greater sense and appreciation for the level of math that the kids are expected to learn at Pear Tree, and how challenging it is, and how in line with the BC curriculum it is in terms of the provincial exams. Like if you look at the provincial exams at grade 10 are not doing grade 10 level math in terms of like trigonometry. They're really doing grade 8 9 math, but in an application or an applied form. And as a result of that, it's extremely challenging for the average high school student. But our students here are doing this all the time. And I guarantee you the average kid coming from another school who all they do is kind of rote formulas could not do what you've just seen here. Whereas our students could do the rote formulas and they could do the application as well. So anyway, I mean, if you have any questions about this, you're welcome to follow up. But I hope from this you have a much bigger appreciation or greater appreciation of what we do at Pear Tree. And this is really just a snapshot of what goes on. So thanks for watching, and we hope to hear from you.